another chapter, which is equation of state. But before I move on, just a quick ask. Does anyone know what equation of states is? What does? So we'll be looking at equation of states from your chemistry background, from some of things you've read, from what you've seen so far. What do you understand by by the term equation of states? Any takers? Hello. Equation of states. What do you understand by that term? That's going to be our emphasis this morning. Any takers? No one. Okay. Okay. From what we've been looking at for quite a bit. Okay. Thank you, Kavir. That's, yeah. So Kavir has said equation of state is PV nRT equal to nRT. So what equation, we'll see that as we move on. So one of the equation of states is what Kavir has mentioned there, which is the equation of state describing ideal gases. So I'm glad that you actually have an idea of what that is. So equation of state, one of them, or the starting one, the fundamental one, is what you've written. Every other thing depends on that equation of state. So I haven't said that. The second question I'm going to ask is, what do you understand? How do real gases differ from ideal gases? How do real gases differ from ideal gases? The equation Kavir has indicated there, that is the equation for ideal gases. That equation describes ideal gases. So the question now is, how do real gases, how are they different from ideal gases? Because that equation only stands, the equation that we have written out by Kavir only stands for ideal gases. So in terms of the real gases, how are they different from ideal gases? Any takers? Any takers? All right, so if there aren't, let's just move on. So a good starting point is where we've started talking about the equation of the equation describing ideal gas. So so as I've mentioned, the one that was written out earlier on, that's specifically for ideal gases. So generally, when we say equation of states, it is an equation that relates your PV and T. So it's an equation that relates your PV and T, your pressure, volume, and temperature. So that is that. So an example is ideal gas, which is your PV equal to nRT or PV equal mRT. But today we'll be looking at other equations. So as I've mentioned earlier on, there's a difference in the behavior of ideal gases and real gases. So based on the difference in the behavior of ideal gases and real gases, the ideal gas equation does not cater for real gases. Can I say that again? Based on the difference in behavior of ideal gas and real gases, the ideal gas equation of PV equal to nRT doesn't cater for real gases. So we need to look for other equations. There are many others, but we'll be emphasizing on three equations that cater for real gases. But before we move on, what are the assumptions? I just want to reiterate that the assumptions for ideal gases, we've talked about that before, but just for emphasis sake. So when we look at there are two main assumptions for ideal gases, which is the fact that the space occupied by the ideal gases are negligible. So in comparison to the in comparison to the actual volume, so the space occupied by ideal gases is negligible. The second assumption is that there are no molecular forces between ideal gases. But when you look at real gases deviate from these two assumptions. So real gases, one is the fact that oftentimes with real gases, the the volume is not negligible. Secondly, for real gases, there are molecular forces. So you have forces pulling them together or forces pulling them apart. We'll be looking at what we call compressibility factor in a short while. Compressibility factor, looking at how, in terms of the different molecules, how are they being pulled apart, or how are they being pulled together. We'll be looking at that. So for real gases, their behavior are totally different from ideal gases. So for this reason, other equations have been come up with, and these equations, they build upon the ideal gas. You remember, we've been, one of the things we keep mentioning is that the essence of ideal is you want a measurement, you want something as a reference point, and then from the reference point you want to look at the reality or the deviation. So that is why you see that for this other equation of states, we'll be looking at Van der Waal equation, Redlich-Kwong, Virial equation. These three equations are built upon the ideal gas equation. So what it's just doing, what this equation, three other equations are doing is that they make provision for what Van der Waal couldn't cater for, and then yeah, so they make equation, and also they do what we call, they factor in, they put in certain factors. Oftentimes we call them correction factors. We call them different names, but usually correction factors. So those correction factors are to cater for what ideal gases do not cater for. One, two, they are also there to emphasize on the fact that from real gases deviate from the ideal gas assumptions. So Van der Waal proposed, so looking at, remember, as we've said, is still, the relationship is still based on P, V, and RT. So the equation still, so for every equation of state, it should still have your P, V, R, and T. So the essence of equation of state is it should relate your P to V and T. So that is the essence of equation of state. Every other thing would then be factors. Every other thing will be constants. So for the Van der Waal, so what it has included are, so the correction factors there. So we have those correction factors for the volume and for the pressure. So the correction factor for the pressure, you see there's an addition, A over V squared. And then for the volume, there is a subtraction. So there's a subtraction for the volume. There's an addition for the pressure. There's a subtraction for the volume. So take note of those two. So there are correction factors. And typically, as we've, the other, like I mentioned at the very beginning, is going to be quite a short class, because the best way to understand most of the things which we've seen from from the onset, is the best way to understand this is through the calculations. So we'll be looking at some calculations over time. All right, so as I've said that, so correction factor, so we have V, so please take note. So your V is molar specific volume. So whenever you are given equations, these are some of the things you need to look out for. So V here is different from, excuse me. So V is different from your typical V. Remember, your typical V will be in meter cube. meter cube. That's what your normally the V that you've been working, the V that you're familiar with will be meter cube. So please take note of that so that when you're having your calculations, you'll be able to make appropriate assumptions, appropriate calculation. But this particular V is called molar specific volume. So you could see mole there. So that is why it is called molar. It is per molar, and it is also called specific because it is per another unit. So oftentimes when something is specific, it is per another unit. So it's not your absolute volume of meter cube. So take note of that. And then for the constants A and B, so these are what they are: your typical critical temperature, your critical pressure. So usually in calculations, as we'll see a couple of examples, you'll be provided with A and B. If you are not provided with A and B, you'll be provided with your RTC PC. So it's either you're provided with this or you're provided with those values in order to get that. So take note of those. So that's let's move on. So remember, like I mentioned, it's so looking at questions, things will get clearer. So what I'm going to do is, as we've done for the other chapter, so put I'm going to upload the PDF calculations. It's been worked out at the moment, and also I'm going to do a video. I will do a video for some of these examples. So please just be patient. I will give me the next couple of weeks, and those things will be sorted. So I believe virtually everything to date have been put online. The only thing that I know that I haven't done for the previous chapter will be for chapter 7. I've not done a recorded worked example, but in terms of the PDF, I've given an explicit, well-described calculation. It's been uploaded, way before we went on break. So please ensure you look through. So like I mentioned, I'm going to do the same for this. So please take note, as I've said earlier on. So okay, here, look at this, for example, what I was alluding to earlier on. Look at this V. So you see that this V will be the V. Let me get the pen out. So we'll see it clearly when we are doing the calculation. You see that this is not your molar, this is not your specific molar volume. So it will be clearer in the subsequent, when we work out the calculations, it will be clearer there. So please take note of that. So let's move on. Let me see if there are any questions so far. So please, if there are any questions as we move on, never hesitate to put them down on the chat panel. Never hesitate to put them down. So the second equation, we've said there are many equations of states, but we'll be emphasizing on three that derive from, we'll be looking at three that derive from the fundamental equation of state, which is the one for ideal gas. All right, so what's the emphasis for the virial equation? So the emphasis for virial equation is Z, this value, the Z. Some call it Z, others call it Z. So whatever you choose to call it, it's the essence is you need to know what it stands for. So that is the main thing about virial equation. Remember, for the previous one, Van der Waal, we've said it incorporates correction factor for pressure and for volume. So what does this one incorporate? It incorporates what we call compressibility factor. Compressibility factor. Then the question is, what is your compressibility factor? I've described them in look at these two ways. You see, it's actually virtually talking about the same thing in different ways, but it's the same thing. So it's the ratio of the actual volume of the gas to the volume of the predicted. So that is what I've shown in this equation here. So the actual volume of the ideal gas has the same pressure as the actual volume. So you take a particular gas. So for example, you have hydrogen, you have helium, whatever, CO2. So you look at the volume, the actual volume of the of that gas, and then you also look at that volume from the perspective of the ideal, that if it were to be ideal, what volume would it occupy? And that's how you get the compressibility factor. So for your ideal gas, your compressibility factor is equal to 1. Your compressibility factor is equal to 1. And why is this? Why is this? The reason for that is, remember the assumption. One, we said there are two assumptions for your ideal gas equation. The second assumption, which is that there are no intermolecular forces. So when there are no intermolecular forces, there is no repulsive force, there is no attractive force. So because of that, the V actual for an ideal gas is the same as the V ideal. So the volume, so if the volume of the gas as actual, the volume of the gas as ideal is equal to is the same. So you have the same value here, the same value there. So the same value at the top, the same value at the bottom, that gives you 1. But for real gases usually deviate from 1. So for real gases, compressibility factor is usually, so for real gases, so we've said this is for ideal gas. So take note, so for real gases, so Z will either be greater than 1 or less than 1. So what I want you to go back and check up, you can easily find this in many materials online. But let me quickly, I've actually, if you check the note on in this lecture slide, if you when you open the lecture slides, I've written additional note at the bottom. So look at the note, but I also want you to do a extra reading up online, that when what happens to the gas when Z, so this is what I want you to look at out for, when Z is less than 1. But I can tell you when Z is greater than 1. When Z is greater than 1, the implication of that is, looking at the intermolecular forces, the repulsive forces are greater than the attractive forces. So if the repulsive forces are greater than the attractive forces, what it means is that it's going to take more force to compress the gas. Does that make sense? So if the repulsive, we talk about repulsive moving away from one another. So if that is higher than attractive forces, that means it's going to take more force to compress the gas. So for a gas with Z greater than 1, it simply implies that the repulsive forces between the molecules are greater than the attractive forces between the molecule. And then the vice versa will be true for when Z is less than 1. But I want you to read more upon that and look at the examples of gases, that obey those different equations, the implications. So please, like I mentioned, I want you to read up on this when Z is less than 1. The second thing I want you to read up on is, how does this factor influence conversion of your gases to liquid? Conversion of gases, we talk about liquefaction, liquefaction. How does your compressibility factor influence liquefaction of your gases? These are some of the things you'll be learning, for example, for oil and gas, in oil and gas, for you to transport your natural gas over a long distance, what they do is they compress it, they liquefy it into liquid. So how does compressibility factor impact on that? Also, I'm sure many of us use perfume, we use spray. When you spray it out, it looks gaseous, but within, you know that it's actually your gas that has been compressed into a liquid. So how does your compressibility factor influence the liquefaction of gases? I want you to read up on that. So please remember that two things. I want you to read up on this. When is Z greater or less than 1? I've talked about it from one perspective. The second thing I want you to read up on is that how does your Z affect liquefaction? So how does your Z affect liquefaction of gases? Any questions so long before I move on? Any questions so long before I move on? All right, none yet. Okay, I still see people still not writing the attendance as per request. The request is your name, surname first, followed by initials as it appears in the MAS. I'm sure also for your ID card, that is how it appears. For everything you do at CPUT, it's usually your surname and initial. So please, let's stick to that for ease, for regularity, for consistency, for ease. And if you haven't put down your, if you haven't filled the attendance yet, kindly do so. So we've said that, and then the additional things that we see that the virial equation, so I've mentioned the fact that we have compressibility factor, I've mentioned the implications of that. The other thing for our virial equations is it incorporates coefficients. So we have coefficients. So look at this, B coefficient B, C, D. So we have coefficients. You remember that from your mathematics. So we call them virial coefficients, virial coefficients. So when it is just two, so when we have those two coefficients, we call them the second term. B and B prime are called second virial coefficients. C and C prime are called third virial coefficients, and so on. It will be clearer in the calculation that I'm going to solve for you later on. So we'll see that. So these are the equations we'll be working with. So we'll be working with this two equations for. So we have the three-term virial equation, we have the two-term virial equation we'll be looking at. That's similar to, for example, you're talking about quadratic equations and the rest. So this will be your quadratic equation here. So that's similar to that, but it will be clearer when you look at the calculations that I'm going to be that I'm going to be providing later on. So please take note of that. So like I said previously as well, you'll always be given those BC, but there are some assumptions you'll not be given that you should know by now. For example, under ideal situation, I'm not going to be giving you that all the time. All you just need to remember, have that at your fingertip by now, is that under ideal gas equation, Z equal to what? 1. And I've given you the reason for that. The reason because those ratio, the volume under ideal condition, the volume under real conditions are the same. So we have that. So the calculation will follow as soon as possible. So the very third one which we'll be looking at is the Redlich-Kwong equation. Redlich-Kwong equation, you could see from the different names that they are named after some particular people. So what I've also done so that I wouldn't keep us for so long in this class is for the things that I've uploaded a video for each of these equation to explain it more. You know, what I'm just emphasizing from today's class is to show you that for all these equations, it's all about P, T, and V. So for all these equations, it's all about P, V, and T. That is what your equation of states imply. It relates those three together, and then there are derivations that I'm not going to take you through, but we'll look through how in the calculations that I'll be working at, we'll look at how do we apply this. So please, once I adjourn the class in the next couple of minutes, go and read up, I'll go and study those videos, because what often happens is once you leave these things for too long, they become overwhelming, and that's when it feels like the lecturer has been giving us too much. And if you were to look at the timetable, we should be having, I think, yeah, it should be 3 hours in a week. But what I've been doing is I've been limiting it to say 1 hour, and I spend longer time working out those equations. They actually take a longer time. So what I want you to do is, one, please go to the videos that I've provided you already. And secondly, secondly, in the next 1 week or so, I'm going to do recorded video screencast casting, screen recording for these calculations. I'm going to upload them. So I want you to look at those videos. And when you have questions, send me a WhatsApp message or email. And remember, by now, you remember the ground rule. Don't send me don't send me WhatsApp questions in the evening. I mean, don't send me WhatsApp text in the evening. Please don't do that. We've said that over and over again. There should be boundaries. So if you have any question regarding, and remember, I expect